including, of course, the average value of the energies, which can be calculated using the following expression. Although this expression looks rather alarming, it's actually quite straightforward. The integrand in the numerator can be thought of as the energy weighted by the probability that the entity will be found with this energy. By integrating over all possible energies, the average value of the energy is obtained. On the other hand, the denominator can be thought of as representing the probability of finding the entity with any energy. Now, the integral in the denominator is straightforward and can be found to be equal to kt. The integral in the numerator requires slightly more work. However, we can use integration by parts by noticing that it is possible to use the product rule to write the following expression. If we then integrate both sides, we see that this is equal to the following expression. A slight rearrangement of this then allows us to integrate the numerator, and we find that the result is equal to kt squared. So putting this all together, we find that the average energy is equal to kt squared divided by kt, which is simply kt, as expected. We are finally in a position to combine our results. We have seen that the number of waves in our cube can be calculated using the density of states function, and we have just seen that the average energy of each wave is given by the equipartition theorem. Now, if we want to calculate the energy density inside the cube, then we need to calculate the energy per unit volume. It is clear that the total energy can be calculated by multiplying the density of states by the average energy per state. And then we can divide by the volume of the cube to find the energy density. This expression can be written as rho of f df, where rho represents the energy density and df the interval of frequencies under investigation. We can simplify this expression and arrive at our final answer for the energy density expressed in terms of frequency. But what if we want to express the energy density in terms of the wavelength? In that case, we can relate the energy density in terms of wavelength to the energy density in terms of frequency using the following expression, where in this expression both rho of f and rho of lambda are positive. The minus sign originates from the fact that df is equal to minus d lambda. And why is this true? Well, this is true because as the frequency of a wave increases, the wavelength decreases, and this is signified by the minus sign. Now we know that the frequency is given by the speed of light divided by the wavelength for an electromagnetic wave, and therefore we can write df by d lambda equals minus c over lambda squared, and then this allows us to write df equals minus c over lambda squared d lambda. Putting this all together, we can then write rho of lambda d lambda equals minus 8 pi f squared kt over c cubed df. Putting in the expressions that we've just arrived, we see that this simplifies, and we can write the final answer as rho of lambda d lambda equals 8 pi kt over lambda to the 4 d lambda, and this represents the energy density in terms of the wavelength. So what does this function look like? If we plot the energy density on the y-axis and the wavelength on the x-axis, then we know what we would like the function to look like, because we have seen from experiment the following smooth curve. However, when Rayleigh and Jeans plotted their function, they found the following alarming result. We see that at small wavelengths, the energy density rapidly increases. This rapid increase can be seen from the energy density. We see that when lambda is small, then lambda to the power of 4 is going to be tiny, and therefore the energy density is going to be huge. If we think about this in terms of frequency, then small wavelength corresponds to high frequency, and since there is no upper limit to the frequency inside our cube, as the frequency tends to infinity, so does the energy density. And it is this catastrophic result that is known as the ultraviolet catastrophe. Rayleigh and Jeans had demonstrated that the best understood classical laws of physics were incapable of describing even the most commonplace phenomena, namely the radiation properties of hot objects. But not all was lost. Out of the ashes of classical physics would emerge a new revolutionary framework that would not only change the laws of physics, but life on Earth itself. Max Planck was an unassuming German physicist who dedicated most of his life to the study of thermodynamics. In a now famous lecture delivered on the 14th of December 1900, Planck announced that the conclusions obtained by Rayleigh and Jeans could be remedied, and the danger of the ultraviolet catastrophe avoided if one postulates that energy can only exist in the form of certain discrete packets called quanta. In order to reach this conclusion, Planck had worked tirelessly on the problem for several years, at times despairing at the difficulties that he encountered. Planck decided to focus in on the experimental results and compare these with the Rayleigh-Jeans curve. Although the Rayleigh-Jeans result breaks down at small wavelength, it actually matches the experimental data quite well for long wavelengths, suggesting that the average energy may indeed be equal to kT in the limit of long wavelengths. On the other hand, it is clear from the experimental data that the average energy should tend to zero for short wavelengths or high frequencies. Planck concluded from the data that the average energy of each wave should depend on the frequency of the wave, and therefore the equipartition of energy should be abandoned. Planck's great contribution came when he realized that he could obtain the required cutoff in energy if he modified the Boltzmann distribution calculation of the average energy. He did this by treating the energy as if it were a discrete variable, instead of the continuous variable of classical physics. In particular, he imagined that the energy could only take certain discrete values, and that the total energy of an object would be an integral multiple of a basic amount of energy. So what effect does this have? Well, it turns out that this has a profound effect on the average energy calculated using the Boltzmann distribution. In particular, the change from continuous to discrete energy corresponds to the replacement of integrals with sums in the average energy equation. So how do we evaluate this expression? Well, the sum in the denominator is relatively straightforward, since we see that this is simply a geometric sum, and so we can write this as 1 over 1 minus e to the minus epsilon over kt. The numerator requires a little more work. Notice that we can implement a neat trick and rewrite the sum in differential form, where we have defined f of epsilon as the same sum appearing in the denominator of the average energy expression. If we then calculate df by d epsilon, we find the following rather ghastly expression. Putting everything together, we find the following expression for the average energy. So what does this all mean? Well, firstly, notice that when epsilon is much smaller than kt, e to the epsilon over kt is very small, and so we can approximate the exponential by the first few terms of the Taylor series expansion of the exponential. This shows us that in the limit of small epsilon, the average energy is simply equal to kt. On the other hand, we see that in the limit of large epsilon, the exponential in the denominator tends to infinity faster than epsilon does in the numerator, and therefore the average energy tends to zero. Now, as we've already seen from an analysis of the experimental data, the average energy tends to kt as the frequency tends to zero, and the average energy tends to zero as the frequency tends to infinity. And we have just seen that from a theoretical analysis, the average energy also tends to kt as epsilon tends to zero, whereas the average energy tends to zero as epsilon tends to infinity. And so by comparing these two sets of observations, Planck realized that whatever epsilon was, it must be an increasing function of frequency. Detailed numerical work by Planck led him to propose that the energy, epsilon, is proportional to the frequency. He then introduced a constant of proportionality so that he could write epsilon equals hf. He was then finally able to rewrite the average energy as hf over e to the hf over kt minus 1. Armed with this new calculation of the average energy, Planck was able to combine this result with the density of states function to derive a new expression for the energy density of a blackbody radiator. Rewriting this in terms of wavelength, he derived the following energy density function. So what does this look like? When Planck plotted his new energy density function, he found remarkable agreement with the experimental data. Furthermore, his function had the added bonus of reducing to the Rayleigh-Jeans energy density function in the limit of long wavelength, as can be seen by looking at the first few terms of the Taylor series expansion of the exponential appearing in the denominator. Detailed experimental work in 1916 by William Koblenz provided wonderful confirmation of Planck's energy density function. The solid line in this graph represents Planck's theoretically predicted curve, and the circles represent the experimental results. Koblenz used his results to determine a value for Planck's constant, h, which is remarkably close to today's accepted value. Despite Planck's work being grounded in the radiation properties of hot objects, his quantum hypothesis would signal the birth of an entire new branch of physics. In particular, his realization that any physical system undergoing simple harmonic motion can only possess energy satisfying the relation E equals NHF would revolutionize how physicists describe the structure of matter. By way of visualizing this, consider the allowed energies in a classical system oscillating sinusoidally with frequency f. In this case, the energy is continuously distributed, as can be seen in the diagram, whereas the allowed energies according to Planck's postulate are discretely distributed, since they can only assume the values NHF. We say that the energy is quantized, with n being the quantum number of an allowed quantum state. 13 years later, Niels Bohr would use Planck's energy quantization hypothesis to develop his energy level model of the atom and kickstart the field of quantum mechanics. Many years later, Planck described his state of mind during those productive years as follows. Briefly summarized, what I did can be described as simply an act of desperation. By nature I am peacefully inclined to reject all doubtful adventures, but by then I'd been wrestling unsuccessfully for 6 years with the problem of equilibrium between radiation and matter, and I knew that this problem was of fundamental importance to physics. A theoretical interpretation, therefore, had to be found at any cost, no matter how high.
Hi everybody, how's everybody doing today? Feeling good? Trying to stay out of the heat? It's much nicer in the studio here. It's very cool. Thanks for the air conditioning, Dave. Appreciate it. Paid our taxes. These guys paid our taxes. Yeah. How's everybody feeling about this stuff? Are you feeling a little overwhelmed these days? Okay, good. That means you're paying attention. You're in the right spot. Okay, this stuff is very challenging. It should be very time-consuming, and just do your best to absorb as much material as you can. The point of this couple of chapters that we've been dealing with is the idea that changing one field affects other fields. Okay, so changing the magnetic field led to a changing of some sort of electric field. We called it the EMF, right? The electromotive force or a voltage. But it's this idea that these things are actually going to talk to each other. Okay, and so this is where we're heading. The next topic, therefore, is just that, electromagnetic waves. Okay, we are now going to combine both of these things, electricity and magnetism, into one concept, electromagnetic waves. So let's talk for a second about the following. Let's say we have a charge, positive charge, and we have a negative charge. And let's say we're going to take these two charges and we're going to move them up and down. Okay? So let's move them vertically. And let's see what happens as a function of time. Well, at one instant of time, they look like that. And if I think about the electric field in between these two, I know what the electric field looks like. It's pointing from the positive to the negative. Okay, I'm just going to draw one line for simplicity. But now, let's move them vertically. So the plus is going to come down, the negative is going to come up. And so at some later time, they're nearly right on top of each other. And at that time, the E field is essentially zero. Okay, there's nowhere I can draw an E field very cleanly. But now let's keep moving them. We're going to put the positive charge all the way down on the bottom and put the negative charge up on the top. And now the E field is pointing up. And so all we're doing is we're taking these positive charges and negative charges, we're putting them together, and then we're going to keep moving them. So now they're the opposite way, and then we're going to come back together again. So now the minus is heading back down, and the positive is heading back up, and eventually they're back to where they started. So if I think about what this E field looks like, it is getting smaller and smaller and eventually zero. And then it flips direction and starts getting bigger and bigger, and now it's a positive. And then it gets smaller and smaller until it's zero, and then it flips direction and gets bigger and bigger until it's again pointing in the negative direction. It sort of oscillates up and down. Okay? And that hopefully looks familiar to you. Right? We like things that oscillate. And if I think about drawing the electric field as a function of time now, what can I say? Well, here it was negative, so it's some negative value. Here it was zero. Here it was positive. Here it was zero. Here it was negative. And so it's going to look something like this. And it oscillates up and down as a function of time. As I move these charges up and down, the electric field is going to oscillate up and down. It's pointing down here. And then it's pointing up here. And then it's pointing down over here. And so forth. A graph like this is just what is the size of the electric field as a function of time. So here, the electric field is zero. Here, the electric field is zero. But at this point, it's a positive number. At this point, it's a negative number. All right, let's go back to this picture here for a second, and let's think about this charge. Okay, charge moving up and down, that is a lot like a current. If I take a wire and I run current up and down, then this current I would look like positive charge heading down and negative charge heading up. These are equivalent pictures. But we know what happens when we have current. What happens when we have current? What do we generate when we have current in a wire? It was the title of a couple chapters ago. Magnetic fields, right? If we have current, we have magnetic fields. I leads to magnetic fields B. And so there is a magnetic field that develops here. How does it develop? Like that. Okay, and you can pick the direction based on the right-hand rule. Remember, you put your thumb in the direction of the current. So stick your thumb down in the direction of the current. Your fingers are going to wrap around in the direction of B. Okay? And so we get a B field that looks like that for this particular picture. That was this case. But when those charges come together, now the current is equal to zero.
Yeah.
And if the current is equal to zero, then B is equal to zero. And later on, as we keep going, the current's going to change direction. The current is going to be going up later on. And if current is going up, we again develop a B field, and you use your right-hand rule, and now it's wrapping around this way. Okay? Thumb in the direction of the current, fingers are wrapping around in the direction of the B field. Okay? Again, it's going to be confusing if you look at me in the glass here, so look at the computer monitor when I do this, and confirm that your thumb going up gets you a B field that wraps around like that. Okay? And when you do it in the monitor, make sure you use your right hand. Does everybody see that one? Okay. So, the charges went up and down. We developed an E that oscillated in time. But now we have a current that's going up and down, and we're going to develop a B that oscillates in time. And so if we draw B as a function of time, it is going into and out of the screen. If I think about just one side of this, B is now going to be like this. Okay? And this is supposed to be coming out of the screen and into the screen over and over again. And we're trying to draw it in the third dimension here.
Да. Я что-то ни хрена не наелся просто. Надо еще, наверное, поесть. Вот давай вместе со мной рассуди, смотри, что надо в жизни. Без чего ты прожить точно не сможешь. Вот просто вот обычная жизнь, я имею в виду. Без денег точно прожить не сможешь, правильно? Все, большую часть всего ты можешь купить на деньги. Все остальное как бы это придаток к размножабельности, думаешь? Ну я не знаю. Ну может все вместе, черт его знает. Ладно, это все сложно, короче. Ну то есть как бы без чего ты прожить не сможешь, да? То есть, естественно, ну да. То есть, да. Но деньги дают тебе, как бы, и откуда ты их будешь брать? То есть, деньги, ну, то есть, труд людской, но мы упростим все вот так вот, просто скажем, да. Это близоруко, конечно, но как бы, но эта близорукость дает тебе гарантию успеха, как сказать, да. Ну, не совсем так. Но, тем не менее, да. То есть, смотри, если ты оторвешься и скажешь, денег мне не надо, то есть, оно уже как бы, оно уже не работает сразу же, да. То есть, как бы, да, если да, понимаю, да. Ну да, то есть как бы деньги и как бы, ну да, ну это все тогда надо, тогда у меня отец правильная была, все, да, сидит в инвалидном кресле и все там. Ну так не бывает. Ну хорошо, за что деньги дают, которые не наказывают? Вот надо быть инвалидом, тогда тебе деньги дают, как эти паниковские там всякие, да. То есть, да, типа того, он просто говорил. Да. Нет, здесь большая разница есть, понимаешь? Да, то есть, да. Я говорю так, ну вот это и было самое, да. Ну это форма тогда попрошайки какая-то, да? Попрошайка. Ну это всегда так. Смотри, даже вот Денис Мацуев, он Мацуев, и он как бы и в славе, и при деньгах только потому, что какое-то время прошло. Да, то есть если ты как бы, да, понимаешь, он тебя, да. Это во-вторых. Да, то есть, ну да, ну понимаешь, короче, я имею в виду, что все одно и то же, то есть, за что художник, да, может это так оно и есть, потому что никто не сможет так сделать, как Мацуев, не туда кто сыграет там и так далее, например, то есть, как бы, ну да, типа того, или, да, ну типа этого тоже так, ну и нахер надо, говорит, награда, он тебя понимает, можно и без этого, типа этого, не имеет в виду. Ну хорошо, тебе можно, никто же тебя не заставляет, как бы, да, он тебя понимает, да. Ну наоборот, это он тебя понимает. То есть, ну, понимаешь, художник, ты стоишь, представь себе, ты стоишь и играешь. Этому не надо, там, да, этому надо, понимает он тебя. Короче, не знаю, что у них там, да, то есть, короче говоря, все равно это надо, и за это платят деньги, понимаешь? Это, ну да, ну не будем мы просто, да, понимаешь. Потом ты, короче, набрал. Что значит набрался? Что это значит набрался? Он о себе так говорит, да, про тебя так думает. Ну это он имеет в виду, да. Не, если ты интересно, я вообще алкоголь не пью, если ты спрашиваешь меня, уже давно, кстати. Я просто, да, ну, он про себя так думает, да. А, что там эти все напихались, и всем все надо. Ну, это не обязательно так даже, понимает он, да. Ну, это он думает там, так, да. Но это не мои уже проблемы, как бы, понимаете. Что ты сейчас, о чем ты сейчас вообще будешь говорить, там, да, понимает? А только пьяных, ты хочешь сказать, что музыка только пьяных людей трогает, классическая, да, или вообще в целом, да, понимаешь, да? Или что там, да. Это утверждение, оно как бы неправильное, да, неправильное, да. Ты считаешь, что ты действительно так думаешь, что оно только такое, да, он про себя говорит, да. Ну да. Ну, это не ну и что, понимаешь, что, то есть оно о себе так думает. Короче, не морочь мне голову, блин, нет. Что она никому не нужна современная. Что ты хочешь сказать-то? Что ты один только такой умный, что ты один только играет такой, да. Он понимает это просто, да. Ну вот это он имеет в виду. Что ты мне мозги ты морочишь, да? Он про себя так думает. Ну это вот он про себя думает просто, да. Меня это не касается, понимаешь? Это не касается, да. Я про себя так думаю тоже, да. Ну, хорошо, ну думай про себя, я вот тебе просто говорю, то есть это, ну он о себе так думает, что ты лезешь, сука, что ты лезешь, блин, ну попрошайка, потому что, да, он о тебе так говорит, потому что, да, нет, я понял уже просто, да, ну, потому что это специфика, да, ну, не, да хватит меня уже цеплять за свои слова, достал, сука, ненавижу. Потому что вот так вот, блин, да. Потому что это специфика просто мастерства такая, да. То есть, значит, все художники попрошайки, значит, да, это во-вторых, ну не так, значит, это просто. Ну не так, потому что, блин. Потому что ты идешь покупать билет в кино, деньги платишь ты за него, кретин, да, без денег тебя полиция заберет оттуда. Тупорылое чмо, блин. Идешь ты на концерт Мацуева, просто так пролезешь, тебя, блин, вот эти про это и говорят они. Чмо долбоебское. Ну и что? И ты о чем? Я тебе про это и говорю, вот, я тебе и говорю. Вот, ну что, да, ну это он имеет в виду. Так ты переворачиваешь наизнанку просто все. Да, он тебя понял уже, потому что деньги художнику дают за то, что он делает что-то, понимаешь, да, типа того, да. Потому что ты, сука, давать не будешь, потому что ты жадное говно там, или просто там, или у тебя свои мнения какие-то, или почему-то, я не знаю, мне насрать. Кто-то другой, значит, даст! Тупорылое говно, и пока, да. Ну так вот, да. Типа того достал. Ну индустрия, так оно и есть уже, потому что там Курт Кобейн какой-нибудь еще в ватяк играл свои 3 аккорда долбоящерских, которые любой удмурт может сыграть. И вокруг него выстроили индустрию.